Okay, take a second to read the problems, lecture problems for Chapter 11. We have a mass oscillating on a spring. We know the spring constant, 305 newtons per meter. We know the amplitude of the spring is going to be 0.28 meters. We know that the mass on the spring is going to be 0.235 kilograms. And lastly, we know that it's going to pass through the equilibrium point, y is equal to 0, with a positive velocity at t is equal to 0. We're asked to describe the motion as a function of time. We have two ways we can do that, either through a cosine of omega times t, angular velocity times time, or with a sine, amplitude sine of angular velocity multiplied by time. Knowing that the position must be equal to, it must be at the equilibrium position, y is equal to 0, at time is equal to 0. This one is going to be equal to the amplitude at t is equal to 0. Cosine of 0 is 1. Sine of 0 is 0, so we want to use this expression right here. All we need is the amplitude, which we have, and the value for omega, which is related to the spring constant and the mass. Simply plugging these guys in, 305 newtons per meter divided by 0.235 kilograms, we're going to come up with our angular velocity of 36.02 radians per second. So we simply write our position as the amplitude, 0.28 meters, multiplied by the sine of 36 multiplied by time. For part B, when is it at its longest and shortest? Well, here I can take a quick look at a diagram of the position versus time for this guy. We know that it's going to go up and come down. That's one full period t. I'll draw another full period t, and I'll draw just half a period right there. So the spring is going to be its longest here, here, and here. It's going to be its shortest here, or here, and here. I know that this is the period t. Point right here is going to be half of t. So it's going to be its longest at 1/4 of the period. It's also going to be its longest at 5 times the period divided by 4. And also right here, we're just going to add one more full period to that guy. It's going to be its shortest at 3 times the period divided by 4, and then add one full period, 7 times the period divided by 4, and we're going to have another point over there where we add another period to 3/4 of the period. We know that the period is related to the angular velocity, such that 2 pi divided by the angular velocity, or 2 pi divided by 36, my period is going to be equal to 0.174 seconds. So my maximums are going to occur at the following times. It's going to occur at 1/4 of the period, which I know what that is, plus an integer value n multiplied by the period, where n is going to be equal to 1, 2, 3, and so on and so forth. That covers all of these maximum and minimas through n number of times. So I could even go ahead and write that as, take the period and stick that in there, the period divided by 4. The maximum times are going to occur at 4.36 times 10 to the minus 2 seconds, plus this integer value n multiplied by 0.174 seconds. So that's going to be my maximums. Same thing for my minimums. Time for the min is going to be equal to 3/4 of the period plus integer values of n multiplied by the period. Go ahead and I plug that in there, where n is equal to 1, 2, 3, so on and so forth. I'm going to get my minimum times to occur at 0.131 seconds plus n multiplied by 0.174, where again n is going to be 1, 2, 3, 4, 5, 6, 7, so on and so forth. Okay, problem 9 gives us some practice on reading graphs. We're asked to find the amplitude, frequency, and period for these two curves, A and B. First, the amplitude, we simply read that off of the position graph. Looks like for A, the amplitude of A is going to be 2.5 meters. And it looks like for B, the amplitude of B is going to be 3.5 meters. So to take a look at the frequency is how many cycles per second. So A is going to cover one full cycle in 4 seconds. So that tells you the frequency of A is going to be one cycle divided by 4 seconds, or 0.25 hertz. B is going to go one full cycle from max to max now in 2 seconds. So the frequency of B is going to be one cycle in 2 seconds, or 0.5 hertz. Lastly, for C, the period, how long does it take the object to undergo one full cycle? That's going to be 1 divided by the frequency, so we could just go ahead and calculate it if we wanted to. Or we can simply say again, for A it's going to be 4 seconds. So the period of A is going to be 4 seconds. And the period for B, the time to go one full cycle, is going to be equal to 2 seconds. And there we have it. Okay, we have a pendulum problem here. I'm going to say I have a pendulum. I know that the period is going to be equal to 1.85 seconds, and that's going to be the period on Earth. We also know gravity on Earth will be 9.8 meters per second squared. And we're asked to find out what the period is going to be on Earth. And we know that the gravity on Mars relative to the gravity on Earth is equal to 0.37. We know that the period of a pendulum is going to depend on two things. It's going to depend on the object's length and the gravity. So here we have the length and the gravity. Now the length of the pendulum is not going to change whether it's on Earth or whether it's on Mars. So I can multiply both sides of this by the square root of gravity and say that the period multiplied by the square root of gravity must be equal to 2 pi multiplied by the square root of length. And this right here is going to be a constant value no matter where you are, as long as it's the same pendulum, the same length. So that's going to be equal to a constant value. What that means is the product of the period and the gravity are going to also be a constant regardless of where the object is. If gravity goes up, the period should go down, and vice versa. So now we can say that the period on Earth is going to be equal to the square root of the gravity times Earth. That's going to be a constant value. That must also be equal to the period on Mars multiplied by the gravity on Mars. Again, this value right here is going to be, or the product of these two must be a constant value because the length is going to be the same. I'm interested in what the period on Mars is, so I'm going to divide both sides by the square root of the gravity on Mars and say the period on Mars is going to be equal to the period on Earth multiplied by the square root of gravity on Earth. Fix that guy. And the gravity on Mars, I know the inverse of that ratio, and I know the period on Earth is 1.85 seconds, so I can simply say 1.85 seconds multiplied by, this is the inverse of that, so I simply say that's going to be 1 divided by 0.37, 0.37, and I'm going to come up with 3 seconds. So the period on Mars is going to be equal to 3 seconds, and that makes sense. The gravity on Mars is less, so it should take a longer time to make one full revolution. The period should be longer on Mars, knowing that the period is multiplied by the square root of gravity must be a constant. Okay, so here I have a wire, or a cord. It's got some mass associated with it, it's got some length associated with it. I know that it's going to be essentially 8 meters long. I know that the mass of the wire is going to be 0.65 kilograms. And I also know that it's stretched with a certain amount of tension that's equal to 120 newtons. And I'm interested in how long it's going to take a pulse to go from one side of it to the other side. So I got my pulse, travels along, finishes right over there. Well, I know very simply that the velocity of the pulse is going to be equal to how far it goes divided by how long it takes it. So I can figure out how long it takes it to travel. It's going to be the speed of the pulse multiplied by how far it goes. How far it goes is going to be 8 meters. Now all I need to know is how fast it's going. So I can take a look and I see that equation 1113 is going to relate the velocity of a pulse on a string to the square root of the tensional force, as well as this mu value, which is simply going to be equal to its mass per unit length. So I could also say the velocity is going to be equal to the square root of the tension force and the mass divided by the length. I know that the length is equal to 8 meters, and I know the mass, so now I know everything that I need to know. Say that the time that it's going to take is going to be the square root of that tension force divided by the mass divided by unit length, all that multiplied by how far it goes. So plugging everything in, my delta time is going to be equal to my 8 meters, that's my delta L, or delta X, multiplied by this tension force, 120 newtons, divided by the mass of the spring, or mass of the string, 0.65 kilograms. Divide that guy by the length of the spring, divided by 8. And all that is going to give me a time of 0.21 seconds. And I could, take this further and say, well, what happens if the tension on the string was doubled? Obviously, you're going to double the velocity of this guy. Just doubling that guy will take half the amount of time. We can talk about longer lengths and so on and so forth if we're interested, but this equation right here is a very powerful equation for describing the velocity of a pulse on a string.